Okay, welcome. Welcome to our lunch seminar series. And today we are very pleased to have my good friend, Professor Morten Hjorth-Jensen from the Department of Physics with us. And Morten will explore how quantum technology and artificial intelligence are shaping the world of tomorrow. And as usual, we'll do a question and answers after the talk, so please stay on for that. But before we start the presentation, we would like really to mention that Morten has recently been made an honorary fellow of the American Association for the Advancement of Science, a scientific organization that publishes the journal Science. And Morten is the third Norwegian to receive this very respected honor. So congratulations, Morten. This is really fabulous news. And then I just hand over the microphone to you. So please.
Hey, can everybody hear me? Thanks for coming. I didn't expect that many people. I hope you won't get disappointed. And by the way, there are actually many more Norwegian fellows. They only list the living ones. So we are more than 3, actually. And if you're not a member anymore, you are not on the official lists. So you have to be a member to be elected. So there's a... But it's a very important organization because it's a amazing voice for science and the scientific dialogue, which we all here, I guess, cherish. Now, I would like to, today, as you can see from the title here, this is not an excess from my side of megalomania. It's simply because this is a topic which I find very interesting, but I will have to bring you on a narrower path when we look at specific applications. But I hope I can give you the kind of gist of what is going on. So the kind of idea is to give you kind of hopefully a pedestrian introduction to why these are interesting topics. And many of you are pretty familiar with machine learning and artificial intelligence, and perhaps less familiar with quantum technologies. So I will try to elucidate what are the pros and cons, and why this can be interesting. Now, when I say we in the slides here, this is again not an excess of megalomania again, but this is simply because there are many, many people which have been involved in these activities. And there are also some, we might say, benevolent benefactors, which I have benefited from. And I was in the US till 24, back and forth, half a year, every year, for 12 years, till my wife said, no, I'm fed up of this. So I'm back in for full time in Norway here. Now, this slide here, if you can read it properly, and I hope you can, gives you a kind of view of many of the things which are going on. So we have artificial intelligence, or machine learning, as I will call it, which is a more precise word for quantum technology, where you actually use machine learning techniques to design an experiment, and that's a pretty hot topic. Then you also have quantum algorithms for machine learning. So quantum machine learning is a very hot and popular field now, an emerging field. We have quantum computing. You will see why these things can be important. And then designing experiments is something which where AI can and really has. It not only can, but actually does a major contribution nowadays. So when you're trying to find the optimal parameters for an experimental setup, using machine learning algorithms is something which is now becoming essential. So if you're looking at accelerator physics, for instance, when you design the beam, this is tightly connected with machine learning algorithms which govern the beam, actually. So these are tons of applications which we benefit from. And one of the things actually I wanted to do, so I took the liberty of bringing up a Menti here. I don't know if you're familiar with that. So if you just go to your cell phones and click on menti.com, and there's a number there on the top. And if you do that, I mean, just feel free to punch it in, and then we can just summarize a little bit afterwards and see how many people have answered. So you go to menti.com, and there's a number which you just need to punch in, And you can just mention at least one significant, perhaps societal importance of AI. So the number is 1961. That's actually the year I was born. 3403. So I'm just going to leave it a little bit so you can see it, and then feel free to punch in the text, and then we can see what people answer, because that's always interesting to see. Everybody gotten it? Those of you who want? Can I change? Okay. So I'm going to go back here. Yeah, I'm just going to wait a little bit more. Okay, so let's go back to the talk. So if you think of machine learning, this is a field which is pretty, mature. And normally we deal with 3 types of machine learning. You will also see other categories later. So typically supervised learning, where you have labeled data. Unsupervised learning, with no labels. There may be patterns you want to uncover. And this is often the typical case when you look at data analysis from big experiments. You have peta or terabytes of data, and you want to find patterns in that. And you have no possibility to label the data. And then there's reinforcement learning, which is a very, very active field of research. And Arne here is actually an active researcher in that field. And the typical workflow is that you have some data, you have a model, you do the train, you train a model, and then you have some functions to assess the quality of the model, and then you make a prediction. That's a typical workflow. Now, when you come to quantum computing, this is a little bit more delicate again, because there are many things which people are not familiar with. Now, if you solve classically a linear problem, then you know that superposition of solutions is something you would typically deal with. So if you have a linear type of differential equations, you can always use the solutions to expand another functions in terms of. And quantum mechanics is, if you think of Schrödinger's equation, is no exception. It's a linear equation in the unknown function you want to find. So superposition is something you have both classically and quantum mechanically. So you can have a system which is lives in a superposition, but then you have something which is called entanglement, which in a way, I like much better the word quantum correlations. But entanglement is one type of quantum correlations. And this is a feature which is being used to both enhance the quality of measurements, if you're looking at quantum sensors, but also to run quantum computations. So I'm going to come back to this. And quantum interference is a very important property. And if you look at this kind of a representation here, this 0 here is a state, and this 1 is another state. So you could think of this as bit 0 and bit 1, and you can make a linear combination here. So this is the superposition. This is just 1, so you cannot make entanglement when you have only 1. And if the systems don't interact, there is also no correlations. So it's like, I mean, in this country, we always used to tease, or it was kind of a joke that during COVID, there was no need to tell Norwegians to keep a distance, because they do keep a distance by nature, right? So the COVID cases were not that many compared to other countries. And when you don't interact, I mean, then there is obviously not much correlations. So the reason why I bring this up is that I will, if I get time, go into a more narrow path where we are looking at platforms for realizing some of these features. And that means experimentally that you're searching for states in a system which you can manipulate. And that's actually the big problem technologically and experimentally, is to find states which live long enough so that you can actually perform operations. Because a quantum computer is something you can think of you manipulating quantum mechanical states. Another thing I wanted to say is that one of the big things which has taken place in the last 30, 40 years is the miniaturization of things. So when I started to study physics, experiments were simply done on huge ensembles, billions or zillions of particles. Nowadays, you can isolate single atoms in small areas, and you can test fundamental properties of quantum mechanical systems experimentally. You can really manipulate single atoms or electrons. A transistor nowadays has just a few electrons. So that means that you can do science at an unprecedented level where you can test many of the basic fundaments of, or axioms of quantum physics. So the big quest is actually to find systems where you can identify states you can label with bits. And then you can manipulate the states with lasers, magnetic fields. And when you do a quantum computation, it's actually you experimentally manipulating a set of physical states. That's what it is. And that's what makes it so difficult to achieve. And also properties like this entanglement, that's not an observable. So that means that you have to set up experimental ways to analyze whether the system was entangled or not. And that's pretty difficult. And then we have quantum machine learning. This is something which has become extremely popular nowadays. So many of the quantum computers you have nowadays cannot realize these huge calculations which you run typically for a neural network. But you can run parts of it. So many of these are hybrid algorithms, which means that you would run a quantum computing part on a quantum computer, but then you have the classical optimization part, which runs on a normal computer. So these are often hybrid systems, and there's quite some interest in finance and in the insurance business, especially in finance. You have many funds like the Norwegian Oil Fund or other ones which invest in quantum computing and quantum machine learning. Because for them, to be first out, to have the best algorithms, means they make more money than the other. So quantum machine learning for finance is a very, very active research field. Now, I just wanted to say some of the benefits, because you have a quantum parallelism, which is an unprecedented way of doing parallelism, entanglement, which is very important, and there are many algorithms which you can show. You can actually have a both better performance, but also less complexity. So how many of you are familiar with Fourier transforms? Okay, so Fourier transforms, if you have, let's say, n states, a standard way you implement a discrete Fourier transform gives you n squared floating point operations. So if you have 2 to the 10 states, this means roughly that you will have 1 million floating point operations. If you do a fast Fourier transform, you can reduce this to 10,000, and that's the standard recipe. If you do a quantum Fourier transform, you can reduce this down to 100. So you can actually reduce this by 4 orders of magnitude. So there is a huge gain if you can implement these quantum algorithms. And Fourier transforms are essential in signal analysis. They're essential in something which is called Shor's algorithm, which really scared everyone who deals with encryption, because you can factorize numbers at a much, much lower computational cost. There are obviously limitations, and I will try to come back to some of these. So you have to rely on states which you can manipulate for a long time enough so that you can set up a simulation. So a simulation of a system is actually you manipulating physical states. And clearly, these states need to live for a certain time in order for you to be able to make the experiment. So when you apply a quantum computer, what you're actually doing is that you're rerunning the experiment many, many times. So calculation means you running an experiment, let's say, 10,000 times on a real physical hardware piece. And you can see also many of the systems are systems which are cooled down to almost absolute zero. And thermal excitations can ruin the computational basis for you. So that's a typical case you will see. If many people work on the same computer, you will get garbage out because the computational basis, this bits 0 and 1, has been ruined or spoiled. So these are many of us. So scalability is a big issue. So even though we don't have an actual quantum computer which can do the fancy calculation we would like to do, there are actually many realizations and technological platforms which are very interesting. So I have my own interest in these things, is that many of these things can lead to fundamental research on basic quantum mechanics, which I am very much interested in. Obviously, the applications are really many. So I wanted to put up some statements on AI and machine learning first. I'm not going to comment them, You can read them, and if you want the slides, you can actually get access to the literature because you can click on the links there. So when I say machine learning or AI, this is not AI without machine learning. So symbolic AI is what you might call the really original one, where you have rule-based derivations of, let's say, specific properties. But this is a collection of algorithms, which you use in the data analysis, making predictions, etc., etc. Also, there's an interesting book by Kate Crawford. She's a professor in sociology from Australia, but she has also been on the board of Microsoft, and she's been studying the ethical aspects of AI. This is actually a very nice textbook, so I recommend it highly. And she has many interesting cases on dubious applications of AI. And also some cases, which I can tell about later, which are less pleasant. So one of the things why we look after quantum computers, if you look at this calculation here of drug discovery, you can see now this is a calculation which run for SARS, the COVID drug design, for 90 days on 250 GPUs and 640 CPU cores. And clearly this shows you that this type of computations are computations which are extremely demanding. So we're obviously looking after ways by which we can speed up this. And clearly if you have a quantum computer, this is a promise that this calculation can be sped up. Another thing which many people don't think of, if you look at all the queries people make on ChatGPT, there's an estimate of the electricity consumption per year. So does anyone remember? So this is 15 terawatt. Does anyone remember how much Norway produces in, what's the electricity production in Norway? That's 150 terawatts. And we use roughly 136. So we export something like 10, 15 terawatts. But you see now, this 117, these are countries on the list. So it's not the sum of 117 countries, but it's the United Nations list. And you go down to country 117 and go down. And these countries actually consume less electricity than all the calls on ChatGPT do annually. You probably know that there is a data science center in Skien in Telemark, which is under construction. And the estimate is that this is going to use something between 6 to 7 terawatt, which means roughly 5% of the Norwegian production is going to this data science center. So clearly, if we can speed up calculations, there's going to be a huge impact on our electricity production. I belong to the people who actually believes that we should reduce consumption and not increase. I did my best after the financial crisis to do that. Okay, so the another way is actually if you look at the type of problems in machine learning with classification, regression, and clustering, these are typical problems which we end up with. And I wanted quickly to just, if you're not too familiar with this, there is a plethora of methods. And the deep learning methods are those which really have, how to say, become perhaps the most popular ones. But we have a whole series of other methods. And I just wanted to say something quickly about the deep learning methods, because we normally distinguish between two general classes of deep learning methods. So one is called discriminative methods, and that's probably the one which most people are familiar with. So this means that if you want to now classify whether your painting is a Van Gogh or not, you would train, for instance, a convolutional neural network. And then when you have trained the model, you can feed it in with a new Van Gogh painting, and then it will tell you either 1 or 0, so as a binary output, and then it will say whether this is a Van Gogh or not. So this is a very classical application of standard deep learning methods or machine learning in general. And machine learning goes from what I call low-level machine learning to the deep learning methods. And this is a pretty common situation, but the one which many of us are much more interested in is actually a generative one. So we have then a data set, and then we are training a probability distribution. So if you look at the traditional machine learning with the discriminative methods, you have a data set, you train a model, and you make predictions, and you can find correlations in the data set. So like if you're looking at housing prices, it's pretty obvious that the number of rooms is strongly correlated with the price of the house, whereas the color of the house is probably less correlated. So these things are things you can extract in a discriminative method, but if you have a generative method, then you can generate new images, for instance, or new data. And the thing then, when you have a probability distribution, is that you can make predictions, you can find correlations, but you can also find the error on the parameters, you can make an estimation of errors, and you can study causation. What is the likelihood of A given B? And for many of the scientific applications, this is the more interesting case. And you have tons of these methods. And some of them deal with a probability explicitly. Variational autoencoders is actually a class of what was called variational Bayesian methods. And then we have energy-based models, diffusion models, and many other models which deal with the probability in different ways. So this is a set of methods which are widely popular and where there is a lot of research now. And then we have reinforcement learning, transfer learning, etc., etc. So I just wanted to give you some of the basics here before we move on. So almost every problem, I should say every problem, starts with a data set you feed in. You make a model. So when you're setting up a deep neural network, that is your model, the architecture of the network. And then you have a function which you use to assess the quality of the model. But at the heart of all these methods, there is an optimization problem because you have sets of parameters you want to optimize. And in the optimization part, there is actually a lot of things to be done. And this is a field where you can get many more new friends. I always used to say that. And I'm not inferring that you don't have friends, but these are friends which will cite you. So there is one popular way to do the optimization, which is an algorithm called ADAM, adaptive momentum. That has more than 200,000 citations since 2014. That says everything. Actually, Kingma, the guy who developed the algorithm, is the same who developed the variational autoencoders. And he's something like 30 years younger than me. So that says everything. The variational autoencoders has just only 50,000 citations. Okay, so you would have a data set, and you would fit a model typically. And data, this is the data, you assume that there is some kind of functional dependence, you can assume some noise, and then you would then fit a model. So this is normally something you will see in every textbook on machine learning and statistical analysis. I used to call this low-level machine learning, because this is something which was developed by Gauss back in 1850. So you would have a linear model in the unknown parameters, and what you would typically do then is to optimize a function, which is typically the mean squared error. And that gives us good old ordinary least squares. And then when you do that, when you optimize this function, you calculate the gradient, what you end up with is an analytical expression where you just need to invert a matrix. And you say that we learn the unknown parameters. Now, you can derive this from a statistical approach. You can start with the probabilities and optimize the probability. And you will get exactly the same equations. So this is normally called low-level machine learning, but it gives you the gist of what enters a standard machine learning method, whether this is a deep neural network or just a simple ordinary least squares. So neural networks, they play a very important role. So they actually, the basic algorithm in many of the more advanced methods, like convolutional neural networks for imaging, regressive neural networks, which is used in natural language processing and as an entry point to large language models. You have autoencoders, etc., etc. So at the heart, there is often just a neural network. And there's an important theory which is called a universal approximation theorem. Like you would have when you look at the error you make when you make a polynomial approximation with a Weierstrass. I always forget the second name there. But the way I want you to think of it is as a universal approximator. Okay? So basically, if you look at the schematic view, this is a kind of single perceptron model. It's very much inspired by neural science. With this one, you cannot fit nonlinear functions. When you have the universal approximation theorem, you can actually fit with a given hidden layer and a given number of nodes. It doesn't tell you what the error is a priori. It tells you you will get a result with a given error. And it doesn't tell you how many nodes you need and how deep the network is. So these become parameters in your model. Then you have the optimization problem. So you have a multi-dimensional beast to optimize and find the optimal parameters. Another situation which is very common is unlabeled data. And then you also have reinforcement learning, where the environment actually helps you in producing a probability distribution. That's one of the possible ways of doing it. I wanted to show you some of the machine learning applications which enter also studies of systems which are relevant for quantum technologies. So there is quite some emphasis nowadays on what we call scientific machine learning, where you actually incorporate algorithms with hardware design and to optimize, let's say, a specific experimental setup. So this is, there are tons of applications from particle physics to medical research to biological research, et cetera, et cetera. So this is a field which is really growing. Another field, so this is just an application, since I come from subatomic physics, this is a field where, so you see the paper is from 2020, so people have actually used neural networks to design accelerator architectures. Another field which is very hot is what's called physics-driven neural network, or PINs. And I will come back to that because we are using that when we solve time-dependent equations for quantum mechanical systems. But this has been a field which is extremely popular in simulations of, let's say, the Navier-Stokes equations, with big success. But I'm coming back to some of the pros and cons there. I'm going to skip some slides. I will skip this one as well, but I wanted now to bring you into a more narrow path. That is what I'm doing. So I hope you can excuse me, because at some time you have to go away from, let's say, the more general thing and then dive into the particular one. So what I'm dealing with is quantum mechanical many-body systems. This is something you would apply to material science, quantum chemistry, subnuclear physics, atomic, nuclear high-energy physics, condensed matter physics. When you design quantum circuits and quantum gates, this is highly relevant. So the overarching motivation is that this type of equations you're dealing with is a multidimensional equation. So if you think of atomic neon, where you have frozen out the nuclear degrees of freedom, you have 10 electrons in 3 dimensions. So that integral is a 30-dimensional integral. So if you had to calculate that integral with standard methods like Gauss-Legendre, Gaussian quadrature, or trapezoidal rule, you will actually, even with few points, you will need more than the lifetime of the universe to calculate that integral. So the basic way you solve these problems is with stochastic integration. So any equation which you have, like Schrödinger's equation, you can rewrite it in many different ways. So you can rewrite it as an eigenvalue problem. You can rewrite it as a stochastic problem. You can rewrite it in terms of coupled partial differential equations. You can rewrite it in terms of matrix inversion problems. So different mathematical recipes give you different methods for solving the problem. And historically, people have always said, my method is much better than yours. So it's always to appreciate the pros and cons of different methods, which is important. So the thing here, in traditional Monte Carlo methods, is that you would try, this T is a trial function, where you make a guess on the system. And then you integrate by Monte Carlo integration. This is essentially what you do. And that's the variational Monte Carlo method. You use the variational principle, and that's it. So technically, it's actually a very straightforward way to solve a quantum mechanical problem. The problem is that you don't have this psi of t. And this function is a function of all the unknown parameters, which you use as optimization parameters. So this is, at the end, it's an optimization problem where you take the gradient of the expectation value of the energy. So obviously, if I have this psi of t, I have solved the problem, and there's no point of me being here. Now, what we have done is actually to replace this one with a neural network. So if you go back to that slide where you can think of a neural network as a universal approximator. So using a neural network will give you a result to a given error. And then you can increase the complexity of the network and see if that gives you better and better results. And it's also, in this field, there is something which is called the, for particles with spin half, these are called fermions, there's something which is called the fermion sign problem, which has always caused problems. Actually, I would say that's a problem which, if you solve that, there is a party in Sweden in December, which you may be able to attend. But when you do this in this way, there is no such problem. And what I wanted to show you are some results for something which is the equation of state for a neutron star. And I have to give you some, so this black line which you see here is a result which is obtained with the best state-of-the-art method, which is called diffusion Monte Carlo. The red one is actually the same approach, but it's not variational. I'm leaving out what that means. And these other things are more mean field methods, like Hartree-Fock theory. So particles see a mean field. So mean fields are not mean. This is actually a mean field. Sorry, couldn't resist that. And you see now with a neural network, with a basic ansatz where you put in the basic symmetries of a system, you get a result which is really on par with the best theoretical results which we have. So that's extremely promising. So why do I insist on this? So I insist on this because if you want to simulate a quantum system relevant for quantum computing, you want to believe that your results are reliable. So the only way we can test this here is that this theory calculation obeys the variational principle, and it gives a result which is better than the best existing calculation. I'm going to skip some of these. This is also another, for those of you who are more from condensed matter physics, this is an evergreen. It's called the electron gas. It's an infinite system. But what you would typically do then is to set up a box with a given number of particles, and then run the calculations, and then the length of the box and number of particles give you the density. And this is also a case where this is actually a strongly correlated system when this radius becomes large. And you see also here that so the number of steps here, for those of you familiar with deep learning methods, this is the number of feed-forward steps and back propagation steps, which you use in the training of the parameters. So in this case, we had a network with 5 hidden layers and 100 nodes in each. And we played around with different activation functions. But you see that the results here, with only baking in symmetries, specific symmetries, because the network has problems. If you don't give the symmetries, it has problems in finding the solution. So you have to give some input. But still, you get results which are amazingly good. So the question now is, since I'm taking you along this narrow path, and seemingly I have only 12, 13 minutes, I want to go to the next part. So, and this is, again, a pretty narrow path where we use machine learning together with standard quantum mechanical methods to devise quantum components for making a quantum computer, or elements of a quantum computer. So what you would typically have then, if you think in terms of reinforcement learning, so this is a quantum device, you have a control part, you have the data which are fed in, and then you have machine learning algorithms which then say something about the state preparation, because you need to prepare the state properly. Parameter estimation, which are the optimal experimental parameters. And then how you interpret data, finding quantum protocols. So all this is a kind of, is a big industry nowadays. And you can replace these quantum mechanical systems with classical systems. There is a paper, if you're interested, which I can, where I took this from. It's a guy from, I think he's Ulm in Germany. Markart is his name. And this is a person who has done a lot of work on applying machine learning to devise optimal experimental setups. And this has again to do with the dimensionality of the problem, because many of these problems, these platforms for making quantum candidates, they are often platforms which are complicated interacting systems with zillions of degrees of freedom. So you can think of, in an overarching way, of deep learning methods as a way to reduce the dimensionality of the problem. There's, by the way, there's a thing I wanted to say here. If you look back at this problem here, So this is an unqualified statement from my side, but it's something which comes from running tons of numerical calculations. So if you think of a parallel, running a calculation with a Monte Carlo integration method, then you know that the error, irrespective of dimension, is the same, which is 1 over the square root of the number of samples. If you use a trapezoidal rule or any of the standard discretization finite difference methods, you will find an increasing error when you increase the dimensionality of the integral. So in Monte Carlo calculations, the error stays the same. But clearly, if you have a multidimensional problem, you need many samples. Now, with neural networks as a universal approximator, if you use it to solve the Navier-Stokes equation, and you compare that with standard finite element methods, the neural network will often not beat the standard finite element methods. This is something which has been refined over decades. But if you go to a multidimensional problem, what we have seen is that that's where the neural network kicks in with its pros and cons, especially its pros, as a universal approximator. So the problems I showed you are actually multidimensional problems with hundreds of degrees of freedom. So as a universal approximator, a neural network, if I use that to solve a low-dimensional problem, I cannot beat the standard methods. Like a Monte Carlo integral cannot beat Gaussian quadrature with dimensions up to 6 or 10, for instance. But a neural network kicks in when the dimensionality becomes large. So it's a way to reduce the dimensionality of the problem. And another thing which is important is actually to understand what it actually means. Because when I fit here, I have 100 nodes in each layer, 5 layers. So I'm getting close to more than 150, 200,000 parameters, which I'm fitting. So the final fit doesn't tell me much. Whereas if I use this method here, this Hartree-Fock method, this is a method where I know exactly what it does mathematically and what kind of physics it gives me. So what you can do then, if you think in terms of explainable AI, is to compare your AI solution or machine learning solution with what you have from before. And then try to interpret what does this bring in terms of new correlations. And that's the way you will often have to proceed, because a neural network, when you look at the results, it's very difficult to actually say what the parameters mean. So just to remind you, so entanglement is an important phenomenon where you have 2 more particles become correlated in such a way that the state of one particle directly affects the state of the other one, regardless of distance. And this feature is actually something which is used in many of these algorithms, especially when we are making quantum gates, where we are manipulating, let's say, 1 or 2 electrons. And for 2-qubit gates, as we call it, you actually need states which can be entangled. These are non-observable properties of a quantum mechanical system. So that means that in order to see that, you need to retrace from the experiment in which state the system was. So in a certain sense, it's not exactly the same, but if you think of the Higgs experiment at CERN, nobody has seen the Higgs, but you've seen tons of experiments or decay patterns which indicate that Higgs was at that specific energy. Nobody has, by the way, seen a free electron. So quantum teleportation is a very important field. So I'm just listing a lot of applications before I'm going to take you into the narrow path. And this is one of the fields. You have quantum key distribution. This is a very, very important field. The encryption industry is one of these fields where, so when you say quantum technologies, this is something which has been going on for 40, 50 years. And it's a huge field with a vast development. So there's a limit to how much we can cover here. Then quantum computing, if you look at something like Shor's algorithm for factoring, this is one of these algorithms where you can have a considerable speed up compared with classical algorithms. The quantum metrology, this is the topic which I'm interested in. And this is a very difficult topic because many of these systems, people don't know actually how to entangle particles and how to use that in sensors. So quantum sensing, you can actually use quantum devices to extract information about the magnetic field. That has an error, which you can estimate because you rerun the experiments many times. But if you have entangled states, you can actually improve the type of error which you have. So decoherence, the states don't live long enough. It's something which is pretty fragile. The interaction with the environment. So many of these quantum computers which we have nowadays, they are, many of them, like superconducting qubit platforms, they're cooled down to roughly 0 Kelvin, which means that if many people are using the system, you can easily break down this computational basis due to thermal excitations. So that's a big problem. So that leads to error corrections. It's difficult to entangle large numbers of qubits. Actually, my main interest, I should say that, in this is to study many-body entanglement in quantum mechanical systems from a fundamental point of view, without thinking of the applications. But there are many interesting applications, obviously. So I'm going to go a little bit quickly through this. So the system, the platform we have been looking at, is a platform which is very interesting, and it has been developed by this colleague of mine from Michigan State. This was taken during COVID. And the way the project started was just by a random encounter before COVID at the coffee bar. So you should not underestimate all the ideas you get by just a random encounter with people. Actually, my best ideas have come just random encounter. And Johannes said, look, hey, Morten, we can now actually isolate a single electron. This device here, with a fridge and everything, is a device, and it's actually down in the basement to avoid, how to say, what do you say when you have movements of the Earth? I don't remember the name of it. So it's cooled down to roughly 0.2 millikelvin. And they can isolate single electrons on layers of superfluid helium. So the nice thing here is that you can use this as candidates for making quantum sensors, because superfluid helium doesn't react if you want to measure a magnetic field, because it's neutral. In this specific case, you can then confine electrons in something which looks like a plain harmonic oscillator. The big problem is actually the readout. So what the experimentalists have done then is that they have run a finite element calculation, and they've made a prototype for what the readout potential looks like. So which we then can feed into the theory calculations. So the system here, you can now trap many electrons. And what we did was to find the optimal experimental parameters using machine learning. Actually, it's not fully machine learning, it's actually plain optimization, but we plan to use more advanced machine learning when we come to more particles. But in this specific system here, you have 2 electrons which can be trapped. They haven't realized this yet experimentally, but we have made the theory calculations with the optimal experimental parameters. And in this case, you can have an electron here in state 0, an excited state 1, and you can have the same here. And this provides a prototypes for entangling 2 electrons. So you have 1 qubit here and 1 here. And this prototype system is the one you would actually try to realize experimentally. They have been able to trap 1 electron, and they know where the electron is. That's very important. Because in quantum mechanics, you don't often know where if the particle is actually in that specific well. So people have tried different platforms. So what we are doing now is actually to look at what's called lateral motion. So this is technical. And this is something which was developed by David Schuster, who was Johannes' PhD supervisor. No, postdoc supervisor. So David Schuster has actually, at the University of Chicago, has done these experiments with superfluid neon and other noble gases, whereas Johannes has developed a technique for superfluid helium. And the whole idea then is that you can set up resonators which you couple with electric fields. So the size of the system is roughly at the micrometers. You can set up electric fields, and then you can generate something which looks like harmonic oscillators by the electric fields. This is the experimental setup. So what we did then was to run theory calculations, where we find the optimal experimental parameters together with an optimization problem, where we then find whether the system is entangled or not. This is essentially what we did. And then the experimentalists can go back, because this is a system where your theory is pretty close to the experiment. It's a system which has basically no influence from the environment, which means that you can really idealize this as an electron in almost a harmonic oscillator lookalike trap. And then you can run your favorite quantum mechanical many-body method. It's actually a two-body problem. And normally we used to call this a baby case in many-body physics. But you can run these calculations pretty easily. And you can then find the tune and find the optimal parameters for entangling two particles. And with that, you can actually create gates, 2-qubit gates. And this is a calculation which Oscar did. I think Oscar is in the audience here. Oscar is doing his PhD on this type of systems. And in this specific case, this is a time, you probably don't see all the details, but this is a time evolution of a system. And in this case here, we start with a ground state, which is a system where we have 2 electrons in the lowest state. Then, by applying a field, we can excite the system, so we have a combination, a linear combination of 1 electron in 0 and 1 in 1, and 1 here in 0 and 1 in 1 here. That's an entangled state. And that makes a so-called swap gate. So by running theory calculations with a time-dependent field which acts on the system, we can actually realize the construction of quantum gates for this specific system. And this is an example in this middle figure here, where you have a linear combination of 2 states which are entangled. So that was just a small demonstration. So I'm getting close to the end. So some observations. So I took you on a very narrow path, but I hope you see the bigger picture, that you can actually use machine learning to actually tune experimental setups, whether this is a quantum mechanical, something relevant for quantum technologies, or whether it's relevant for other types of applications. So I find this an extremely useful method to find out which correlations. So you may ask, why correlations? Now, the correlations tells me something about the underlying forces. And at the end, when you study the equation of motions, you want to understand which are the underlying forces which govern the system. And hopefully, you want a simple message so that you can tell your grandmother. Actually, my grandmother, till she passed away, she always kept asking me, Morten, what are you doing? And then I was close to 50. And every time she said, what are you doing? And then I told her what I'm doing. And she said, yeah, but what are you doing really? So I think to find something simple out of complex systems is one of the things which drives me, and to understand nature. And since these are multidimensional problems, machine learning really comes to our aid. In both the design of experiments, but also in theory simulations, where you cannot run an experiment because you know how to run the experiment, but you don't know which are the relevant parameters. So what we did for these experimentalists is actually to find the relevant parameters. They know how to make the system. They have all the fine-tuning, they know all the fine details, but they don't know exactly which are the parameters which are of interest. I hope you see the kind of broader picture here. So these are just things which I am interested in, and also how do we use entanglement in various quantum platforms? Can we use AI, ML for better design? I have always been, obsessed with the educational efforts, for those who know me. And I think this becomes even more important nowadays because it has also to do with the literacy of the population. And at the very, very end, for the development of democracies, if you want to put it in a longer perspective. Having a fundamental understanding of what this means is crucial. So let's, before we go here, let's see if people have answered. Yeah, okay, let's see here. This is fantastic. So it's protein folding, healthcare, finding cancer, protein folding, health science, efficient production, healthcare. You see there are many, many healthcare things. Peace, software development, synthetic biology. This is fantastic. Thanks for filling in this. Better medicines, pattern recognition, efficient researching tools, doing my homework. That's also important. Actually, this is a very important topic, to have people use it efficiently, because then you can really tackle the big, interesting scientific problems. I am very much fond of using these tools in education. So better recommendation, that's also a good point. Maybe I should screen my recommendation letters through ChatGPT. Good. Life and living beings, optimization, work in natural language, improvement, fantastic. Thanks everybody for that. So, but you see, one recurring theme is health. So the Chinese company Alibaba, and this is what I wanted to end with, they have invested massively in machine learning. And there's a very important reason for that. It's because China has a coverage of medical doctors which is much smaller than what we have in Western Europe, which means that a pathologist, when you have to go through screens of tumors, this can take 1 or 2 days. And you know that the pathologist, this is also a shortage, we have a shortage here as well as pathologists, is something which takes a life to train. So if you can then screen the tumors by machine learning methods, and then say this is a benign one, this is a malignant one, and then you leave the dubious one to the pathologist, then you can save a lot of time. So if running the machine learning algorithm through a scan takes some few seconds, and then you rule out the bad cases, and then you have a specific treatment for the benign tumors, this is something which really helps a lot. So I would say for me, one of the big benefits, that's my personal one, as many of you have stated, is actually the applications to healthcare. Another one which is interesting is actually, I belong to the people who think that tax is not a 4-letter word which begins with F. It's we have had a group of students who have gotten jobs with the Norwegian IRS, Skattedirektoratet, and the Norwegian IRS has developed a quite efficient department on using machine learning on the tax declaration, and especially searching for tax fraud. So we had a student who actually got a job there, and he's now leading one of these departments. And he said in the beginning they had to train the models against some biases, like the typical tax evader was a male, a little bit younger than me, 50 plus something, living in the western part of Oslo, white. So these were typical biases in the system. So they have developed efficient software which actually gives the Norwegian IRS more money with a small investment. And that's a huge benefit to all of us, because hopefully some of this money go back to research. Hopefully. But these answers here are just fantastic. 39 responses. Really, thank you, guys. Let me just, I think I shouldn't say more here. Oops. Let's see if we can click it. There we are. There are probably tons of things I've forgotten. Thanks for coming, and thanks for filling in that form. Thanks.
Well, thank you very much, Morten. This was really an exciting and broad-spanning presentation. And now we have some time for questions. So please feel free to ask. I had to take off my glasses so I can really see. Are there any questions? Yes.
Thank you, Morten, for nice presentation.
Good to see you again.
Yes, see again. You was my lecturer, and I was failed first attempt to take exam with you. But anyway, thank you.
No, but you did excellently. You did actually.
Yeah, so thank you. I have a question regarding my particular work. You mentioned that deep neural network can replace or at a multidimensional problem for Navier-Stokes equation. However, is it possible to employ in some kind quantum computing in effective way for Navier-Stokes equation? Do we have any ideas, or maybe you can?
So there are actually people. The thing with these two fields, I mean, the fields are huge, and one of the problems which I feel is like So 1 year ago, I would have said no, but actually I found a paper which did this. And if you look at many of the scientific papers, you get a little bit biased in the sense that if something is 10 years old now, you're thinking of archaeological times because the field moves so swiftly. But actually, this is being done now. The problem is that you would still use a hybrid algorithm to do that, which means that you would implement some of the parts on a quantum computer. And normally, if you think of quantum machine learning algorithms, you can actually do only the very small data sets. So it's still not something which is comparable to what you would get with your finite element method.
For example, if we are using quantum annealing.
Quantum annealing, I don't know about, but I think that's an interesting path. I think that's a good idea, Sergey. I think so. I think, yeah.
More questions?
Yeah.
One down there. A question? There, yeah. Jonas?
I just have I need maybe a little bit more elaboration on the usage of pins, because I was introduced to it a little when taking your course at the beginning of my master's, and I really saw the efficient use of trial solutions when trying to model these specific, say, heat equation or wave equation, whatever it is. And obviously, you referred to it now when you were talking about the wave equation and doing Monte Carlo simulations and everything. And in the name pins, it's obviously physics informed. So you have to add some physics to the network to make it learn. And I suppose that the trial solution then becomes very reasonable and valid to use in this network. But how do you really come up with a trial solution when, say, the system is so complex, and say the equations that you're monitoring are also very high dimensional?
So this is an excellent question, because this is actually what we are planning to do now. So the input to the network is now you having studied the ground state or an excited state of the system with a standard Monte Carlo methods with a deep neural network. So that if you get a very good estimate for the states, then you have a pre-trained network. And you would transfer that information to the physics-informed neural network, where you would do the time evolution, and where you then would bake in a time-dependent interaction which acts on the system. Because training such a pins can become very difficult if you don't know what you should look after. So having done the static calculation, which we call, or just the structure one without time dependence, serves as you preparing a state or a neural network, which then can be fed into the pins calculations. So this is exactly where we are now. So this is a very good question, because if we want to study, so people have studied, for this system of electrons, they've studied many-body entanglement using finite element methods. But this is something you cannot push beyond two particles in 2 dimensions, because it's a 4-dimensional plus time. So that becomes quickly a very heavy calculation with a finite element method. So that means that you need other methods which can tackle the big dimensionalities. So again, the kind of keyword is dimensionality reduction. So how can we keep track of the relevant degrees of freedom so we can actually handle a problem? And all of science deals with finding effective degrees of freedom at the very end. At the very end, that's what we do. And sometimes we have reliable ways of linking effective degrees of freedom, and sometimes we just use ad hoc intuition. There was another question here,
Yeah,
Vidar,
yeah.
I think.
Yes. Down there. You get a microphone.
Yes, very interesting. It's actually related to this problem here, because so you said that with the normal Monte Carlo method, the error scales as 1 over the square root of n. Yeah. It's not. Is it possible to compare the results that you obtained with the neural network to that scaling? Like, is it possible to say something about how those methods compare?
So this is one of the things also we want to do, because these are pretty recent calculations. So we actually in this type of analysis part now, actually, we've also tried to extract the interesting physics. What does it mean? What does a network mean? Because one thing is to run the calculation, the other thing is to ask, what does it mean? And so we haven't tested that, but that's one of the things which is on the...
How would you even do it? Like, how do you compare, like,
No, you would simply run with different types of layers. I mean, just adjust the parameters and see if you get this roughly 1/n error scaling. That's roughly what we would do in a very empirical way.
Way behind?
Yeah.
Yes? Others? Is it? Yeah, I think so.
Hello, and thank you for a very interesting talk. I'm wondering about how close we are technologically to solve the temperature problem when it comes to introduction of noise into real application of quantum computing. What's your most optimistic assessment or speculation on it?
I have basically no idea, unfortunately. So the noise problem is something which is a pretty hard one to deal with. And also the system we have been studying is a system which is cooled down to almost 0 Kelvin, which means that you can actually run calculations in a quantum mechanical regime, which again means that also since you don't have much influence from the environment, is that you can neglect any thermal excitations. But in real systems, if you look at the point defects which are being studied experimentally here, these are systems at room temperature. And that means that you need to include temperature in one way or the other one in the modeling of the system to understand how much it influences. So this is a little bit back to this kind of general philosophy, because these are complicated many-particle systems, and when you add temperature, it becomes even more complicated for the traditional, let's say, quantum mechanical description. So I would say that this is a problem we will have to carry with us for some years to come. So I don't think there is I don't see an immediate solution. Yeah.
Okay.
Perhaps that's another one of these settings which will bring you to meet the Swedish king in December.
More questions?
Yeah, okay.
Okay, we have to finish. Thank you for all the interesting feedback, and also online here. And thank you all for coming. I would like to say also that next week we will be joined by Jonathan Adams from the Institute of Health and Society in the dScience launch. That's down in the building between the buildings over there. And he will give a talk on structured methods and principles of the ethics of AI in healthcare. So that's also related to healthcare and AI. And you will find the full program on our website, and also feel free to grab some food if there is something left. There is, yes, fine. So please do that. And let's just give another applause for the speaker today, Morten. Thank you very much.